Well, good morning, everyone. This is Penny from Wisconsin Land and Water, and thanks for joining the ethics webinar today. And we're not taping this webinar, so it's going to be a live interactive webinar. You can unmute yourself during the presentation and ask questions anytime. We want it to be really interactive, or you can send something to the chat line and ask your questions there, and we'll be trying to watch that for questions as they come up. So we're taking questions anytime. You don't have to wait till the end of the presentation. We'll also take them at the end. And I think that's about it. I'm gonna turn it over to Janet.
Thanks, Penny. This is Janet Vosberg, NRCS Engineer in Richland Center. Welcome to the 2019 Engineering Ethics Training. All right, so just a real brief thing, why are we doing this? Chapter AE 13 covers continuing education for PEs. Every couple of years, every 2 years, we have to get 30 hours of PDH to keep up our licensing for Wisconsin. And during that 2-year period, minimum of 2 PDHs has to be professional conduct and ethics. Just another interesting thing, the 13 of those 30 have to be interactive. So these today would count as one of those 13 as well. So I didn't know this, but if you have an excess of PDHs, you can carry over up to 15 into the next biennium. And then in your first registration cycle, I guess you don't need the 30 hours of continuing education. I don't know if there's anyone out there that has it. We might have a couple people on that fall into that category. So, but chapter 13 is what covers all of this, if you want more information on that. So just wanted to point out the professional societies, they have their ethics or whatever, and that's usually the ones we see when we do our ethics training. And that's, just an example of one is shown on the right side there, how they list their ethics. Just to be clear though, Wisconsin AE8 actually covers professional conduct and is the law that binds us on what's considered professional conduct. And, they overlap somewhat, but I just wanted to point out that there on the right is the actual state law portion that is the obligation for professional engineers. And you'll see different professional societies have their own ethics, and although they overlap, there is an actual state law that covers our professional conduct as engineers. This is out of AE 13. This is just an example of a document that you can use to keep track of your PDHs. This is the one they recommend. Doesn't have to be this one, but just wanted to throw out an example of something you could use to keep track of your PDHs. So, and then the website where you can find that is listed down below there. So now we're going to do case study 1. It's a video, and Scott is going to run that and then lead a discussion afterwards on the video. Thanks, Scott.
I'm Alan J McDonald, and I am currently an aerospace consultant and author of a book called Truth, Lies, and O-Rings Inside the Space Shuttle Challenger Disaster. At the time of the Challenger disaster, I was the director of the Space Shuttle Solid Rocket Motor Project for Morton Thiokol, the manufacturers of the large solid rocket boosters on the shuttle. I'm going to discuss the Challenger accident, how the launch evolved, what happened to the Challenger during its launch, and some of the inquisition that happened as a result of the investigation by a presidential commission on the accident. The Challenger disaster happened on the morning of January 28, 1986. It took place on pad 39B at the Kennedy Space Center in Florida. I received a telephone call from a fellow that worked for me. And he said, Al, he says, we were just told that there was a weather forecaster, I believe in Orlando, that was forecasting a cold front in the area of Florida that might drop temperatures as low as 18 degrees Fahrenheit by tomorrow morning. And we're really concerned about whether the O-ring seals and these fuel joints of the solid rocket booster will operate at those temperatures properly. And I said, well, I'm very concerned about that too. They said, Al, what you need to do for us is get a hold of somebody at the Cape there from NASA to find out what they're projecting hour by hour all through the night at the launch site, not in Orlando, so that we can calculate what the actual temperature will be on various parts of our boosters by the opening of the launch window. I says, I will get that information and call it back to you. But I said, when you get it, here's what I want you to do. I want you to get the engineers together and have them make an assessment of their concerns of the cold temperatures on the sealing of those O-ring seals. And I would like them to make a recommendation as what is the lowest, safest temperature to launch that we can tolerate. And I want that decision and recommendation to be made by the Vice President of Engineering, not program management. I felt that that was a thorny technical issue and should be decided on its technical merits only. And as a result, I requested that the Vice President of Engineering make that recommendation. So I called the NASA rep there and arranged for that teleconference that evening. And it was a three-way teleconference between the engineers in Utah, those of NASA in Alabama, and our management at the Kennedy Space Center in Florida. So it was not surprising to me that after the engineers presented their information, the Vice President of Engineering came on just as I requested and recommended that they do not launch the Challenger below 53 degrees Fahrenheit, which was primarily based on that observation of that flight a year earlier. The NASA management really didn't accept that conclusion and felt that if we're going to change the launch commit criteria, we needed to anchor it in something better than just this qualitative observation. And here was a condition which we had claimed as, in our opinion, going in a direction that may well cause a failure, a very catastrophic failure. And so what happened is that my boss, Mr. Joe Kilminster, who was the Vice President of Space Booster Programs, came on the telecon and asked for a 5-minute offline caucus to make sure that we had presented everything that we had available to us and see if we could better analyze the joint to determine if there was a lower temperature that was safe to launch. What really surprised me was that when the management of my company came back on a half hour later on the teleconference, it wasn't the Vice President of Engineering anymore who made the recommendation not to launch below 53 degrees Fahrenheit. It was my boss, the Vice President of Space Booster Programs, Head of Program Management. And he said that they had reassessed all of their data and they have concluded that it's okay to proceed with the launch as planned. No restrictions at all, no temperature requirement whatsoever. Well, NASA's reaction was that, well, they accepted that without any question, but they needed that recommendation put in writing and signed by a responsible Thiokol official. Well, I knew who that responsible Thiokol official was. That was me. That's why I was there. And I made the smartest decision I ever made in my lifetime. I refused to sign it. Now, I didn't think it was totally unethical that the NASA people questioned how we arrived at that decision and the data we presented. What was unethical is they knew that we had a moral obligation to always prove it was safe. And what they had just done was put the engineering people in a position to prove that it would fail. That's a totally different question. You're never supposed to do that. And in fact, the final decision, which I didn't know at the time, I found out later, was that the general manager decided not to listen to the engineers who still felt that it was too risky and tried to convince him not to change the decision, even though he thought that NASA had some good questions and he kind of agreed with them. He decided that he was going to poll his management team, which ended up as only the vice presidents, as to whether we should launch or not. Now, this was, at the time, all unknown to me because I was back at the Cape. But I was so disturbed with the change in the launch recommendation, and we were waiting for the written recommendation to come back from our plant in Utah, that I turned to the NASA management people and I said, I really don't feel comfortable with that decision. I don't agree with it. But more importantly, you cannot even accept that recommendation. And they says, what do you mean, Al? I said, you cannot accept it because you know, and I know, that you're asking us to fly those solid rocket motors outside a temperature it's been qualified to fly in. And you can't do that. You can't fly any of the shuttle hardware outside of its qualification limits. That's against protocol, so you can't accept it. I'm recommending launching not based on what I know, but what I do not know, and you're in exactly the same position. And they said, Al, these shouldn't be your concerns, but we'll pass them on in an advisory capacity only. And they said, where's this fax that's signed by your official? And it so happened the fax machine was the other end of the building, so I went down there, and it took a while to come in, but I finally brought it back. And when I brought it back, they were in a teleconference with one of the people on the mission management team. Since I was gone for 15, 20 minutes, I presume they talked about the O-ring issue earlier. And I was shocked to find out later they never mentioned it. Well, I remember getting up early that morning of the launch, and I was carrying my briefcase in one hand and my headset in the other, going to Launch Control Center. And I remember hearing on the radio it was 22 degrees Fahrenheit at the time. I went into the Launch Control Center and sat down at a console that I'm supposed to be at to monitor all the data on the solid rocket boosters. And in the corner of that TV monitor that I have, they have access to various cameras that are on the vehicle that you can punch in and look at. I remember I started looking at some of the cameras, and I noticed there was ice hanging on the vehicle, there was ice hanging on platforms next to it, and I quickly concluded to myself, well, they aren't going to launch this thing today. And the next thing I noticed was several minutes later, they decided to send an ice team out to the launch platform to knock down as much of the ice they possibly could and take it off the mobile launch platform because they're concerned of debris. And they did that. And after they did that, they picked up the count again, and they finally made another stop in the count to go back and send the ICE team again to re-look at the launch pad, and they did. Came back and concluded that it was okay to proceed with the launch, which really surprised me, but they did. Now, I really expected if the O-rings would fail because of cold temperature, they would do it right at ignition when you would light these solid rocket boosters. Strangely enough, some 73 seconds later, the whole vehicle looked like it had exploded in the air. And I was watching it on the TV camera with one eye on the pressure tracers of solid rocket boosters and the data we were monitoring. And it was absolutely shocking to everyone that was in their control room. I could hear some people actually sobbing in the background because they knew that this was unsurvivable. I went to Huntsville, Alabama, the NASA Marshall Space Flight Center next morning to be part of the failure analysis team that NASA was forming on the solid rockets. And I was about convinced that, yeah, this was caused by, in my opinion, I thought it probably was a cracked turbine blade in the Space Shuttle main engines finally came loose because they were having that problem and went through the tank, and that caused the explosion, or the tank structurally came apart and exploded. And I was ready to leave and go home because I've been gone for about a week, and I actually walked out the door and was heading out the door, And this fellow from NASA that I argued with the night before, by the name of Larry Malloy, said, Al, you need to get back in here. I says, why? He says, we've got Jim Kingsbury, the Director of Science and Engineering for Marshall, that's at the Cape looking at some movies and films of the launch. And he claims he can see some fire coming out of the side of one of your solid rocket boosters just before the explosion. My heart sank when I saw the actual launch film, because I thought, you know, it probably did happen exactly for the reason we were concerned the night before the launch. The O-rings were too cold. And it wasn't until President Reagan decided to form a presidential commission where the real answers came out, and primarily from me, not NASA. What had happened is I stayed and worked on that failure team, and within a few days, I presented to NASA exactly how the Challenger failed. And it was due to the cold O-ring issue that we had addressed the night before. It just manifested itself in a final failure quite different than we expected. But that's why it really failed. It was clear that they didn't want to hear that. And what had happened was one of the NASA people in Washington, who was a budget analyst, had sent a memo he had written to the New York Times. And it was about this problem that we had with this O-rings and the joints. Well, at that time, NASA had never briefed the Presidential Commission on anything that caused the accident at all. They knew nothing about any. And yet, it was almost a week earlier, I'd briefed them exactly what caused it. So they scheduled a closed hearing that afternoon with NASA. Well, NASA wanted all my charts that I had given to headquarters the previous summer, and I gave it to them. And I remember going up to this briefing, and it was in the old executive office building next to the White House. And the NASA folks made it very clear they were going to give the entire briefing. No one else needed to make any comments unless they were specifically requested to do so. And the fellow who was briefing was a fellow I argued with, and he was going through these charts, and he briefed for about an hour and a half, and the commission asked for a break. They took a break. They came back, and I remember Dr. Sally Ride, before she sat down, she was thumbing through a bunch of pink telephone slips. She says, before we get back to the briefing, because the guy was going to read, I'd like to ask you a question. I returned a few of my phone calls. And one of them was some reporter here in Washington that asked me if it was really true. They'd heard a rumor that one of the contractors may have been concerned about the cold temperatures affecting their hardware. May have even recommended not launching. Is that really true? In fact, he said, we had a teleconference about their concerns of the projected temperatures on the field joints and O-rings. And as a result of that teleconference, we had all our engineers in communication with all our engineers in Alabama and the management at Kennedy, and reviewed all that. And as a result of that conference, Martin Thiokol recommended that we proceed on with the launch as planned. And they submitted a written statement to that effect. And went back to his briefing. And I thought, well, I guess that's a true statement, but that is about misleading as anything I ever saw, and was certainly unethical. And so I finally started walking down the stairs towards the conference table that the commissioners were sitting at. And Mr. Larry Malloy was giving this briefing, was giving one of the charts that I'd given him, in fact, that morning. He was being asked some questions about it. He said, I think Al McDonald has something to add here. I said, I think this commission should know that Martin Thiokol was so concerned about the projected cold temperatures on our field joints and O-rings that we recommended not launching below 53 degrees Fahrenheit. I remember Chairman William Rogers, who was the head of the Presidential Commission, and his vice chairman, who was Neil Armstrong, and Dr. Richard Feynman. They all kind of stood up and trying to peek at who this guy was coming down here. And William Rogers was the ex-Secretary of State under Nixon and Attorney General under Eisenhower. And he looked at me and he says, well, who in the hell are you? He said, would you please come down here on the floor and repeat what I think I heard? Because if I heard what I think I heard, this will be in litigation for years to come. My life changed when he said that, because I knew who was going to be in the middle of all of this litigation for years to come. Me. Looking back at all the decisions and things that happened, there's two criteria I always look at with regard to ethics. There's ethics that are associated with having to make tough decisions, tough pressure, time constraints in that environment, and then there's those that aren't, which I consider those, frankly, are the worst ethical issues. And both of those occurred in the Challenger decision. I'm proud of what I did, but as far as ethics was concerned, the biggest breach of ethics was the fact that both my company and NASA attempted to cover up what really happened that night before the launch. And there was obfuscation by NASA on what really caused the final accident, which I went over with the Presidential Commission before they filed the report, and they agreed with me. And to me, that was a bigger error than the pressure at the time to launch from a breach of ethics, because they had time to think about it and deceive people. One of the big disappointments I had after going through all that, and a lot of the lessons that were learned from Challenger and were fairly well implemented immediately after, but they carried over to a point where they finally were forgotten some 17 years later. When they launched the Columbia that year in 2003, they clearly saw on the film this huge piece of foam, it was called ramp foam, off the tank impact the orbiter. And it actually impacted the leading edge rather than under the tile and shattered. They then ran some analysis of what that impact damage could be, and they had the fanciest, most up-to-date computer model there was available at that time in 2003, and concluded that the damage wasn't significant enough that they couldn't return home safely. There were some engineers at Langley that didn't feel comfortable that that was the case and said, well, we can find out for sure by asking the Department of Defense to turn one of their spy satellites towards the orbiter in orbit, facing towards it, and it will see it in spades if it has significant damage that it would be a catastrophic reentry. So they made a specific request to the mission management team to do that. And it so happened that the mission management team declined that request on the basis that they'd had an analysis done by Boeing on this crater model computer program that was the most fancy thing in the world, and that they don't feel that it was adequate damage, so they didn't need to go through the protocol and all to make a request to make these pictures. It was the first time in the 50-year history of NASA that I saw they went from a can-do attitude to a can't-do, and that was the most serious mistake and the most unethical mistake I think they probably made in their entire history. One of the lessons learned I tell students also is this: don't always believe in all your big computer programs. Use your gut feeling and some back-of-the-envelope test of reasonableness checks on some of those answers, because that will give you far more confidence. And I tell you, some people have better judgment just saying, you know, it doesn't smell right, and you need to do that. And so that's the other lesson learned. And don't presume anything. If you think it's important, make sure that what you thought was important got to the right people. So that's what I wished I would have done.
So, how many of you remember the accident?
Yeah, this is Matt. I remember being in grade school and watching it live on TV in the classroom.
Yeah, same here. This is Matt.
And there's some people that are on chat line. Kevin Kirsch remembers it. Bernie Macau does. Mike O'Shea saw from a distance. So I don't know if he was there. So that they responded in the chat line.
Sounds good. So I challenge you to look at the three people. The one that I want to kind of focus on is the management, the program management team that sent the memo. What do you think they're thinking the next day or morning of?
This is Bart. Litigation, both criminal and civil.
Yeah, the hindsight, you know, after whatever time of the morning that was, I don't remember, but it probably went pretty quickly. What did we do? Okay, so Janet did a
One more
wonderful.
thing on that, Scott. This is Janet. Yeah, so, you know, it was interesting. He said, you know, prove it would fail. You know, that's what they were challenging him to do. You know, in moving on with everything, he had to prove it would fail. That's not really a good operating model.
Proving the negative is absolutely.
It
So,
seems like management was hunting for reasons to okay the launch rather than, you know, taking a neutral stance and looking at it. They were probably more interested in, you know, saving costs by not delaying the launch rather than putting a priority on safety.
Holding paramount to public safety?
Yeah, well, safety should have been the top priority, and they were more interested in just sticking with their timeline.
Yeah, this next video will get into that, so we'll hop into that real quick.
Five, four, three, two, one. Liftoff. We have liftoff.
When it's my life on the line, what type of a team do I want out there holding it in their palm? And the answer I came to is, I think, the identical answer you would come to in the identical circumstance. When your life is on the line, you're going to want a team that's the best holding it in their palm. And how do teams get to be the best? They get there by practicing fundamentals, by doing little things consistently and religiously day in and day out until they become as natural as breathing. You don't even think about them. Now, there's lots of fundamentals out there, but there are three that I think have overarching importance to the success and safety of all teams everywhere, and those are the three that I want to talk about this morning. When I'm involved with any team, but particularly when there are lethal consequences associated with the team environment, as there are with you in firefighting and emergency response, just as it is in the space program. People die when they don't understand the dangers of a normalization of deviance and protect themselves against that. And I'm going to talk about that. I'll define that here for you in just a moment. I want everybody on the team understanding the essence of responsibility as it applies to the individual as well as it applies to the leadership. And I want a team that's filled with courageous self-leaders. I think Harold really kind of hit on that in his earlier comments. It's self-leadership that determines how safe and successful you can be. It's looking deep inside yourself. It has to be everybody practicing self-leadership for the team to succeed. It can't be 99 out of 100. Every individual, again, particularly in hazardous environments, has to be a courageous self-leader. So I'll talk about that as part of this teamwork program. Now, I'm going to use some experiences I had both as an Air Force flyer and as a NASA astronaut to develop some points on these fundamentals. And sadly, NASA provides me with two great tragedies to draw from to make some points. Those tragedies being the Challenger disaster and the Columbia disaster. Now, Columbia occurred 4 years ago. I think everybody's kind of familiar with that disaster. During launch, some foam came off the gas tank, damaged the heat shield. 2 weeks later, Columbia burned up on reentry, killing 7 astronauts. People are probably familiar with that disaster, whereas Challenger goes back 21 years ago this past January. Long time in the past. So I imagine most of you are probably foggy in your memories what caused the Challenger to be lost. And because I will be referencing that program, referencing that disaster in this program, I want to take a moment to briefly review for you mechanically what caused the loss of the Space Shuttle Challenger. Challenger was a failure of the right-hand solid rocket booster. These things are so big, they're 150 feet long, 12 feet in diameter, and each of them weighs 1.3 million pounds. They're too big to be made in one piece at the factory in Utah and shipped in one piece down to Florida, where they're launched. So they build them in 4 propellant-filled pieces that are shipped separately by flatbed rail car from the Thiokol plant in Utah down to the vertical assembly building at Cape Kennedy. There, these segments are stacked on top of each other to form twin towers of boosters. The gas tank is hung between the boosters. The The wing vehicle is attached to the gas tank, and then all of this is taken out to the launch pad on this 9 million pound mobile launch platform. Now, when these boosters ignite, they burn at 5,000 degrees Fahrenheit and at a pressure of about 1,000 psi. Steel boils at 5,000 degrees. So you have to ensure in your design that the steel of the booster is never touched by the fire that it contains. So there's insulating material to run the inside length of these segments. The obvious weak point in this design is where you've bolted these segments together, because there you have a potential leak path for the gas to pass to the outside, melt the steel, and cause a catastrophe. Now, I'm not going to go into the engineering specifics of the joint design that was intended to prevent such gas leakage, other than to say it was based on a redundant flexible O-ring scheme. 2 flexible O-rings. Here's a piece of one of them right here, 12 foot in diameter at each perimeter of those segment joints. 2 of them at each joint were supposed to form a redundant steel-to-steel pressure seal to prevent the fire from leaking out. On Challenger, both O-rings failed on the bottom segment of the right side solid rocket booster. Here's Challenger coming off the launch pad. In that yellow area, you'll see a black smoke being ejected. That's the vaporized O-rings being shoved out that bottom joint. You now have 5,000 degrees eating into that outer wall. As the rocket flies higher, the gas is vaporizing a bigger and bigger hole in the side of the booster rocket. 73 seconds into flight, the rocket comes apart, killing the 7 astronauts. Now, what you're seeing here appears to be an explosion, but was not. This was a catastrophic structural breakup. The fire weakened the attachment to the bottom of the gas tank. That bottom just basically fell off. The top of the booster rotated into the top of the gas tank, rupturing that, and under the aerodynamic and G-loads of the moment, the vehicle just shredded itself. Nothing detonated, nothing blew up. That will become important to remember downstream when we talk about crew survivability associated with this tragedy. Now, you're going to need that background to understand some of my downstream comments, and certainly you're going to need it to understand my comments about normalization of deviance. What is this? Well, it's that natural human tendency, particularly in pressure circumstances, to want to take shortcuts, to accept a lower standard of performance. Maybe it's a lower standard of personal performance, a lower standard of performance for some team you lead, lower standard of performance for some machine firefighting equipment that you oversee. But it's very human to find yourself in pressure circumstances, and God knows you folks find it on every call. Very human to find yourself in a pressure circumstance and rationalize, I can't execute to meet these standards I've been trained to meet. I'm going to have to take a shortcut. Maybe the shortcut is what Harold was talking about, not doing a proper risk assessment. Maybe it's not having the right communication in place. Maybe it's not wearing the right protective equipment, whatever. But it's very human in pressure to rationalize, I can't do this job and meet the standards. I'm going to have to take a shortcut. And so you take that shortcut. And guess what the consequences are? There are no bad consequences. You aren't injured. Nobody's injured. The emergency response proceeds successfully. There are no bad consequences to your actions in taking that shortcut. What's that going to do? It's going to loop it back into your brain and reinforce the rightness of that earlier decision to take the shortcut in the first place. So what's liable to happen the very next time you find yourself in these same pressure circumstances? And I guarantee there's going to be a next time, particularly in your businesses. Because there were no bad consequences the last time you took the shortcut, you're going to be mightily tempted to do it again. You do it enough times, and what happens? The shortcut becomes the norm. Here are the standards that you're expected to be meeting. Here's where you are in execution. This deviance is invisible to you. You don't even think about it. It has become normalized into your actions, into your team actions. And what happens with normalization of deviance, it leads to predictable surprises. And if you ever want, and I'll tell you, in hazardous environments, predictable surprises on the job can be injurious and they can be deadly. If you ever want an object lesson in what normalization of deviance can do, a predictable surprise, look at Challenger. Challenger was no accident. Challenger was a predictable surprise. At the time that rocket came apart, scattered throughout NASA contractors and filing cabinets and desk drawers were written documents, memos, predicting that the exact thing that did happen, i.e. failure of this O-ring, was going to happen. And where did people get the information to make such predictions? From the best source available, flight data. It doesn't get any better than to get the piece back and see how it performed. And that's the case with these solid rocket boosters. They're not throwaway items. 25 miles up, they burn out, they're jettisoned, they have gigantic parachutes that are deployed. These things are lowered into the water. Air is trapped inside them when they hit, so they float. Tugboats are positioned out there to put a line on them, tow them back to shore. There, they're cleaned up, taken apart, inspected, and used over again. The operative word in this process is inspected. You know, on 14 of 24 flights before Challenger, Challenger was number 25. On 14 of 24 flights before Challenger, in the inspection process, quality assurance and safety people noted that the O-rings, which were never designed to be touched by fire, were being touched by fire. And they understood the ramifications of their findings. This design is flawed. It's going to fail. People are going to die. And they basically put words to that effect in these various memos. I want to share with you excerpts of two of these memos, both of which were written by Thiokol engineers, the contractor, to their customer, NASA. The first memo was dated February of '84. This is 2 years before Challenger. And in part, the memo reads, "The recent experience of 2 burned O-rings on STS-11, that's the 11th shuttle mission, raises concerns with STS-13. You know, when I read this, I wonder how come nobody was concerned about STS-12, my first mission. But apparently they weren't. The O-ring leak check procedure is also an urgent concern. Your support in this urgent matter is requested." 2 years before Challenger, the label urgent has been hung on this O-ring design. It's not working. Here's a sentence out of a Thiokol memo dated July of '85. This is 6 months before Challenger. The memo was written by Mr. Roger Bougielet, a Thiokol rocket engineer. In his memo, he wrote a very prophetic sentence. Here it is. "It is my honest and very real fear that if we do not take immediate action to dedicate a team to solve the problem with the field joint," and that's the O-ring, "having the #1 priority, then we stand in jeopardy of losing a flight, a crew, and all the launch pad facilities." Mr. Bougielet's prediction was only off 73 seconds. He thought the rocket was going to blow up on the launch pad, destroy the vehicle, kill the crew, and take out the launch pad facilities. He missed it by 73 seconds. Challenger was no accident. Challenger was a predictable surprise. Now, I know what everybody's thinking right now. Why didn't the team react to these warnings, ground the fleet, and fix the problem? And the answer is, to a significant degree, the team was laboring under a long-term normalization of deviance. And let me explain. Approximately a decade before Challenger, a standard of performance was established for these O-rings in our failure modes and effects analysis document. They were given a Criticality 1 label, meaning if they ever fail, it's loss of the vehicle and death to the crew. So a standard of performance was established for these O-rings. They can never show any hint of a failure mode. If they fail, it's death. And de facto, you have now established a standard of performance on how the team should react if they ever see a problem with the O-rings. Criticality 1 deviance, only one thing you can do, ground the fleet. But that standard of performance was established, as I said, about a decade before Challenger in a no-pressure situation. Emphasis on those words. When the first O-ring damage is seen, it's not a no-pressure situation. First O-ring damage is seen when they get the boosters back from the second shuttle mission. Now here you have leadership, quality assurance, safety people staring at their worst nightmare, evidence of a major design flaw in this multi-billion-dollar program. And they can see how the standard of performance has been violated. This is a Criticality 1 deviance we're looking at, a burned O-ring. And at that point, the standard for the team was what? Ground the fleet. You cannot fly with a Criticality 1 deviance. But the team could not bring themselves to adhere to that standard of performance established those many years earlier. Why? Because it's not a no-pressure situation. These people are a tremendous pressure, not just to see the fleet continue to fly, but to rapidly expand the shuttle flight rate. It's laughable now to hear, folks, but you know where we were headed in the early 80s with the shuttle flight rate? 26 missions a year. A shuttle was going to be flying every 2 weeks. And in fact, the shuttle made no economic sense if it wasn't flying at that flight rate. NASA had promised Congress and the American public the shuttle would dramatically reduce the cost of operating in space because it was going to be so easy to turn between missions. It would just take a couple weeks from landing to get it back on the launch pad with new boosters, new gas tank, new payload, and it's ready to go again. And that business model, 26 missions a year, became our God. Nothing could get in the way of that schedule. So now the team is facing a Criticality 1 deviance. They have a standard of performance that they're supposed to adhere to, ground the fleet. But under this tremendous pressure, they start rationalizing why they can continue to fly or how to take a shortcut, to accept a lower standard of performance. What they do is they take a pristine O-ring, they intentionally damage it to a degree greater than what they saw in the damaged recovered O-ring. They put that intentionally damaged O-ring in a laboratory pressure test article. They pressurized it to 3,000 psi, 3 times the pressure it ever see in flight, and that damaged O-ring held pressure. So the team rationalized, hey, even a damaged O-ring is holding pressure, and in flight the backup O-ring held pressure, so we don't need to ground the fleet. We can make some minor assembly processes and hope that fixes the problem, collect some data on the fly. We can continue flight operations in spite of a criticality 1 deviance. So they take the shortcut. And while I'm telling this story, I hope all of you are thinking about how many times you have rationalized. We're all human. We all come under pressure. How many times have you rationalized it's okay to take the shortcut? So now here the NASA team has rationalized it's okay to take the shortcut. You know, what they've done here now is accepted something that was never expected. It wasn't that the O-rings were designed to take damage and continue to function. They were never to see damage. But in this pressure cooker, the team has rationalized why it's okay to see some damage, something that's not expected and not understood, and flight operations continue. And guess what the consequences are? There are no bad consequences. The next couple missions return pristine O-rings. Boosters that show pristine O-rings. And every time they break apart one of those boosters, see those perfect O-rings, what's that doing? Looping back into the brains of the NASA team, it was okay to take the shortcut in the first place. Then they get the boosters back from the 6th shuttle mission. They see more damaged O-rings. What happens now? We're deeper into the program, the expectations are higher, the promises have been made are greater. Harder now to go back to that original standard of performance that says ground the fleet. And now they have that history of having gotten away with in the past. It becomes a little bit easier to rationalize why it's okay to continue flight operations again. So they make some more minor assembly process changes and continue flight operations. Basically what's happening here, folks, is the damage seen on Flight 2 is slowly becoming the umbrella. And the team slowly starts rationalizing, as long as we never see damage that exceeds what we saw on Flight 2, it's okay to continue flight operations. Well, for another dozen times or so, they get back boosters where the damage to the O-rings doesn't exceed what they saw on Flight 2, until on Flight 25, Challenger's mission, the damage exceeds in a great way what they saw on Flight 2. Total primary and backup O-ring failure, loss of the vehicle, and the death of 7 astronauts. Basically, by the time Challenger was occurring, a large body of the team that was working this O-ring problem had come to expect to see O-ring damage. Now, I want you to think about that. We'd gone from something we had correctly defined as intolerable to accept to something over 4 years and 24 missions has become what? Expected. Normalization of deviance. It is a killer of teams, folks. Literally, in hazardous environments, it will kill people.
So, a little more background on what we had talked about, normalization of deviance. Janet had sent out the pre-homework for you. What do you think of what you read with the oil in the deep water out in the Gulf of Mexico?
Hey, Scott, I think they're real similar in the fact that, you know, as long as nothing bad happened, they accepted that as a success. And so, like the case study that we read about wrote, is that it's almost predictable that something bad is going to happen eventually, because that's the only way that those errors are going to manifest themselves.
Yeah, and also, you know, both situations, you know, they were well outside of what was considered normal or good operating procedure, and just the lack of anything bad happening just pushed them onward.
With the second written example you gave, it didn't go into as much detail. I think what was striking with the second video you showed is that how early on the O-ring failure was actually being observed. So it wasn't just a theoretical, like we've gone beyond the operating standards in a theoretical sense. It's that they'd actually observed failure within the operating confines.
Very true. I hope people are going through their own minds thinking, where in my private life and my work life do I do the same thing, and have gotten away with it. just kind of let that one mull around as we keep continuing and moving down with more examples here.
And now that we know what normalization of deviance is, I want to discuss how we protect ourselves against it. The first line of defense is recognizing our vulnerability. You're not any different than those engineers at NASA. We're all human. We all come under pressure on the job. We all get tempted to take the shortcut, to accept the lower standard of performance. So recognize your vulnerability. I just used, by the way, this NASA disaster to drive home what normalization of deviance is. But let's remember, it happens at an individual level, it happens at the smallest team levels, it happens in all industries. If you want an example, again, Harold touched on this, an example of normalization of deviance at the individual level, it's not latching a seatbelt. Why do people not latch a seatbelt? Because they've gotten away with it for 10, 20, 30, 50 years. They've driven and never needed it. That deviance is invisible to them. They've normalized it into their behavior. Do yourself a favor and your families a favor. You get in those vehicles, latch those seat belts. But we're all vulnerable, and that's the first line of defense. And another thing I'd implore all of you on these, you make multiple responses to emergencies. You can fall into the mode of believing you're so good. You're so good. You're bulletproof. And you got to recognize that's not true. There's no history being created. When you respond to an emergency out there and you successfully execute, there's no history being created in the laws of physics, the physics of death that you deal with. Fire, explosions, collapses, things like that. There's no history out there that's remembering how good you were the last time and is now going to cut you some slack the next time. It's up to you to recognize your vulnerability. First line of defense. Execute to meet standards. We have an expression in military aviation to protect us from normalization of deviance. It's called plan the flight, fly the plan. For you folks, it's plan the work, work the plan. Execute to meet standards. We have an expression in military aviation that the flight manual of a modern fighter is written in blood. It's very true, because there are people who have paid with their lives to learn some aspect of the operation of this vehicle, of this plane. And now that entry is in the plan to protect our lives. And it's exactly the same in your business. There's a huge memory out there of mistakes that have been made in the past that are incorporated now in your procedures. They are there to protect your lives. But it only works when you execute the plan. You meet those standards. Consider your instincts and the instincts of the people that you lead. Obviously, we have instincts for a reason, and sometimes they can be dead on accurate. Obviously, from reading from these memos, there were a body of people, particularly at Thicol, that were not affected with this normalization of deviance phenomena. Well, let me tell you what happened in the midnight hour, literally the midnight hour before Challenger was launched. Some of the authors of these same memos convened a special teleconference with their NASA counterparts and pleaded with them to call off Challenger's launch because the temperatures were going to be very cold, and the engineers rationalized these O-rings were going to get stiff, lose their flexibility to seal those joints when the boosters ignited, and a catastrophic leak could develop. So they pleaded with their counterparts at NASA to call off the launch until it got warmer. What was the response on NASA's end of that teleconference? They hammered these engineers. Show me the data! I can't call off a launch just because you don't feel good about it. Show me the data. We've launched in cold temperatures before, nothing bad's happened. Show me the data. They didn't have the data. It would have taken tens of millions of dollars offline testing to get the data. Instinctually, they had great fear what was going to happen if their product was used in these cold temperatures, but they had no hard data to support those instinctual fears, and their instinctual fears were dismissed out of hand. Don't do that, folks. We have instincts for a reason. If you're out there on one of these emergency responses and there's something nibbling at you, this just doesn't look right, something is wrong here, listen to that voice. Take a moment, stand back, and see if there isn't some data to support that instinctual concern. If you're in a team leadership position and your people are coming to you and say, hey, boss, this just doesn't look right, there's something here that just doesn't feel right, listen. Take a moment, look, and see if there isn't some data to support that instinctual concern. Don't dismiss those instinctual concerns out of hand. Finally, I would make sure that everybody archives and reviews the near misses and disasters that have occurred on your teams and within your industry. And God knows there's lots lots of disasters out there to learn from, and Harold talked about a lot of them that you've recently had. But let's make sure we don't repeat the mistakes. Oh, you know, that's the greatest tragedy, when you see mistakes repeated. And somebody somewhere else in the industry has already paid with an injury or a death to learn something, and now it's repeated by some other part of the firefighting teams out there. Make certain that you archive and review the near misses and disasters that have occurred. New hires should be required to review them. Everybody should be required to review those lessons periodically. This, by the way, was not done at NASA. 17 years, this is the real tragedy of Challenger. 17 years later, it was all repeated. Normalization of deviance is what brought down Columbia. Now, what happened on Columbia is a piece of foam flew back, hit the left leading edge wing, which has a carbon panel on it. The wings and nose see 3,000 degree heat on reentry. They're protected with carbon panels. In tests that were done after Columbia, they fired some of this foam into panels of this carbon, and they blew holes in it. And that's what happened on Columbia. They had a 9-inch diameter hole on reentry. There was a pathway for 3,000 degree heat to enter into an aluminum vehicle that melts at 1,000 degrees. The left wing burned off, the vehicle tumbled out of control, broke up, and 7 more astronauts died. And what you're looking at here, folks, is another example of normalization of deviance at work. Here's a comment made by one of the Columbia board members. NASA had lived for 20 years with the idea that foam, the foam on the gas tank, could not cause a catastrophe. Foam appeared on lists of critical safety risks for every flight, but its defects were given a standing waiver. Normalization of deviance. The lessons of Challenger were forgotten. 7 more astronauts died 17 years later. So let's make sure we practice these fundamentals right here to guard ourselves against that normalization of deviance. We are all vulnerable in hazardous environments that can lead to injury and death. I want to talk about the fundamental of responsibility, and I want to introduce this topic by telling you a story from my Air Force flying career. I have to preface the story with this point. I was not an Air Force fighter pilot for this reason right here. My eyes were bad. I had to wear glasses. So I flew in the back seat of fighters, the F-4 Phantom mostly. If you saw the movie Top Gun, remember Tom Cruise was Maverick? His backseater's call sign was Goose. That's what I was. I was an Air Force Goose flying in the back of these F-4s. Now, I wasn't married to Meg Ryan like the Goose in the movie was, which, by the way, is her great loss, or so I would like to believe. Okay, the story I want to relate to you right now involves my very first flight in this airplane, the F-111. This has side-by-side seating. The Goose rides the right side of the pilot. I was making my first flight in this airplane, doing some weapons testing over the Gulf of Mexico. In the course of that weapons test, we reached a point called bingo fuel. Bingo fuel is a safety point. You calculate it before you ever take off. It's the fuel state at which you're supposed to stop the mission and fly home, because theoretically at bingo fuel you only have enough gas to do that. Safely cruise back to your base, attempt to land, not be able to land because the weather's bad, feels close for some reason, and have to divert to another base maybe 100 miles away or so. So bingo fuel was a safety point. I knew that. I had 1,500 hours of goose time from the back of the F-4 that told me that. Now here I am on my first flight in this airplane staring at bingo fuel. I pointed out the pilot on my left expecting him to fly home, but we had one more data point to get in this weapons test. And he said, looked at me and said, we can get this last data point. Okay. So we sailed past that safety point. I'll cut to the chase. The airplane that took off looking like this, and which cost us taxpayers tens of millions of dollars, ended the mission as this pile of wreckage on the Eglin Field runway. And I wish I could tell you there were some heroics involved here, but there weren't. We ran out of gas. And as the plane was crashing, I reached for the ejection handle and pulled it. On the F-111, that separates the entire cockpit. The crew remains inside. A parachute is catapulted out, and the cockpit is lowered to the ground. In our case, the ground was the runway. So we were close, but close only counts in horseshoes and hand grenades. It doesn't count landing one of these jets. Now, what does this story have to do with responsibility? Well, I'll bet everybody here can see where I'm going with this story. I want everybody to come back into the cockpit with me at that moment in the flight where we reached bingo fuel. I pointed out that pilot at my left expecting him to fly home, but instead he looked at me and said, we can get this last data point. And even though at that critical moment there was this little voice whispering in the back of my brain, oh, Mullane, this doesn't look right. We don't have a lot of gas. We're sucking it down in a big hurry. We're 70 miles out over the water, long way from home. The weather's bad back home. This doesn't look right. Say something. Put your perspective on the situation out there on the table for this guy to consider. but I didn't say a word. Basically, at this critical moment in this team operation, I ceased to be a team member and became what? A passenger. And why did I do it? Well, let me tell you, for the identical reason in your past lives, you've done the same thing. This is the original sin of teamwork. We're all guilty of it. You may not have done it in a long time, and hopefully you'll never do it again, but I guarantee each and every one of you can remember back in moments in your careers where you were seeing something. You were sitting in a meeting and hearing something. Maybe you had an idea, you had a concern, but just as I did in that F-111, you sat there mute. You didn't say a word. You became a passenger, and then years later, or maybe weeks, months, even years later, you regret it. Because now you can see that something bad happened out here that might not have happened had you maintained your team presence and put your idea or concern out on the table for the team and the leadership to consider those many weeks, months, and even years earlier. Why do we do this? And I'll tell you, it can happen in a heartbeat. We're going from effective team member, next moment, we're sitting there as passengers. There's lots of reasons, but here are some of the real whoops, I'm getting ahead of myself here. One of the major reasons is we end up in that mode of wanting to accept this group think. We'll sit there and go along with the flow with a group, whereas individually we would never agree to accept it. You know, we'd have, if somebody came to us individually and asked our opinion, we would have that opinion. We'd put it out there. But in a group, we don't want to deal with confrontation. It's easy to go with the flow. You know, that group think. That'll turn us into a passenger. We assume others are going to take action. We don't need to. We defer to people who have been in the organization longer and occupy loftier positions, rationalizing they have to know better than we. You know, that's what turned me into in that F-111, that's what turned me into a passenger. I was the goose. I had 30 minutes of flying time in this plane. The pilot to my left had 1,000 hours in it, and he was the aircraft commander. So I rationalized at that bingo fuel point that, hey, he's got to know what he's doing. He's got so much time in the plane. He is the aircraft commander. Surely he sees the situation more clearly than I. And so I deferred to him, position and longevity. And disaster resulted. My near death, his near death, and the loss of that plane. These are just some of the reasons that we can slip into this passenger mode. And I tell you, when it happens, the team is jeopardized. If everybody is not on board with the team, if we have any passengers on the team is jeopardized. This right here is the irreducible essence of our responsibility as individuals on a team, right here, is making sure we count. We never slip into that passenger mode. The power of all teams, folks, resides in the individual. And I say that, it's the engine, the individual is the power of the team. And the reason I can say that is none of us are clones. We've had this diversity of life experience. And through this diversity of life experience, we bring a diversity of perspectives to team situations. You may have 99 people on a team, and because of their common life experience, they have a common perspective. And then you have one other individual who worked somewhere else, was on a different team, had a different boss, had something happen to them in their past lives that is now giving them a different perspective on the situation. And if they would maintain their team presence, put it out there for the team and the leadership to consider, it could have a measurable and significant impact on the safety and success of the team. But it only works when 100 out of 100 people are doing it, not 99 out of 100. Maintaining that team presence. And I would encourage everybody, when you talk about individual responsibility, to tattoo this quote on your brain. This is a quote by former U.S. President Andrew Jackson. One person with courage forms a majority. And that's very true. Another way people dismiss themselves into the passenger mode is assuming they don't count. The team's too big. You know, nobody's going to hear them. And they dismiss themselves into that passenger mode. Everybody counts, folks, because none of us are clones. And we all bring this diversity of life experience to the team that gives us this diversity of perspectives. So let's remember that. You count. I don't care if you've been on the job day one or if you're getting ready to retire after 30 years. You count because you are not replicated anywhere else on that team. And I would encourage leaders to make sure they lead with this philosophy, empowerment, to make sure in word and deed you're telling your teams, hey, I value you as an individual. I recognize your uniqueness, that you're not duplicated. If I'm going to lead this team and be in the safest and the most successful it can be, I have to climb into your brains and take a look around. I want to hear from you. That is a critical aspect of leadership, and that's empowerment, making sure nobody is allowed to slip into that passenger mode, that everybody counts.
Okay, so that is that video. We do have one more that we're not going to do here. So let me flip back to the other phone here. Okay, so did we pick up some things on ethics today and our responsibilities? Any other thoughts?
Yeah, this is Bart. Last couple field seasons, I've been construction inspection on a large dam removal project in Michigan. And every day started with our pre-dawn safety meeting. And this was a crew of, I'd say, 20 operators and field techs, probably about 10 pieces of heavy equipment on the ground. And we had a really good safety officer. But the safety meetings are so simplistic and so mundane. And you can just see after a few weeks of getting into the construction that operators are getting complacent and just kind of bored with the safety meeting every single morning. But it just reminds me that by reminding us every morning, it put it in the forefront of our thoughts of safety.
Yeah, and I would add to that, you know, the ethics as engineers we hold, and to remind ourselves of those daily. I know there's a few of us in the agency that have gone through the order of the engineer, and having that ring on your signing pinky is a good reminder daily of those ethics and our responsibilities to the general public. So I want to just chime in here and say, Janet, I appreciate you pulling the videos together and the PowerPoint and making this easy on me. So thank you for your work and effort. Penny, do you have anything to add? I have one thing to add after that. Penny, anything from you?
No, I just sent out in the chat a reminder that if you do want a PDH certificate and you're online, to send me an email so we know that. And I also sent the link for a short evaluation that people could fill out. And thanks to Janet and Scott for working through this webinar and making it a success.
Wonderful. The one thing I'm going to add is we didn't get to this fourth video on courageous self-leadership. I think it's worth your time to listen to. It's not necessarily ethics related so much. It's more of a inspirational part of the speech that Mike continues with, but I found it funny and enjoyable and definitely inspirational. So I would take the time and watch it. So thank you very much, guys.
Thanks, everyone. And thanks again, Scott and Janet. Have a great day, everyone.
Okay, let's finish up this program now with a discussion on courageous self-leadership. And again, that goes back to what Harold was talking about in his opening comments about looking deep inside yourself and seeing, you know, have you become complacent? Can you change yourself? Can you be better as a team member and better as a team leader? That all goes back to courageous self-leadership. The success and safety that you enjoy is not through luck. It's not written in the stars. It's not destiny. Personal and professional success to a significant degree flows from courageous self-leadership. I hear all the time when I interview with the press and they hear my life story, and I'll tell you here in a moment how I turned out to be an astronaut, but when they hear that story, I look at the paper the next morning, the first sentence will read, "It was destiny that Mike Mullane would be an astronaut." No! No! Destiny has nothing to do with personal and professional success. It's not written in the stars. Flows through courageous self-leadership. I'll prove to you that it wasn't destiny that made Mike Mullane an astronaut. This is what destiny had to work with right here. Teenage Mike Mullane. Trust me, you would not have wanted him knocking on your doors and dating your daughters. That put the fear of God in you. You know, a lot of people assume if I'm an astronaut now, destiny had genius to work with. Gosh, I have to have been a gifted genius child if I'm an astronaut now. Well, let's investigate that. Here's my high school yearbook photo. Down in ambition, it says to attend the Air Force Academy. I couldn't get into the Air Force Academy. My grades weren't good enough. West Point took me, which frankly doesn't say a lot about West Point. But in all fairness to West Point, I was a third alternate for my congressional district. I barely made it into West Point, and at graduation West Point, I wasn't on the stage getting any awards for academic excellence. Destiny did not have genius to work with. Let me show you a few other things that Destiny struggled with. This is the varsity club in my high school, the star athletes in my high school. Ladies and gentlemen, I'm not in this picture. Destiny didn't have athleticism to work with. See this lady? This is the homecoming queen. I didn't date the homecoming queen. Destiny didn't have good looks to work with. This next slide says it all, what Destiny had in teenage Mike Mullane, the autographed pages out of my high school yearbook. It gets worse. It gets worse. I have one autograph, one. And you know what it reads? And I'm as serious as a heart attack. It reads, "You missed Korea, but here's hoping you make Vietnam." That is the only autograph I have in my entire high school yearbook. Destiny did not have popularity to work with. Folks, I am not an astronaut because it was written in the stars, because it was destiny. And you have not led your teams to great success and safety. You, as an individual, have not achieved success and safety because it was destiny, because it was luck, because it was written in the stars. It's because you learned and practiced elements of courageous self-leadership. We all learn these lessons from many different sources. Parents are frequently a great source. Coaches, teachers, scoutmasters, co-workers, bosses. We learn these lessons, we apply them, and from that flows great success. And I learned my lessons, significant lessons, from my parents. My dad was a World War II aviator, met and married my mom when she was 18 in 1943. My dad survived the war, came back to live the American dream with my mom, but then in 1955, at age 33, my dad was crippled for life with polio. Never again walked, spent the rest of his life on crutches and braces and in a wheelchair. And at this time in my parents' lives, they had 6 children to raise. I'm number 2 in the birth order underneath that red arrow there. But you can imagine the horror of waking up one day and realizing the primary breadwinner in a family of 6 kids is now confined for life to a wheelchair at a time in America where impaired people were not highly valued. And this could have gone down real ugly. My father could have committed suicide, could have become a drug addict, my mom could have left him, but none of that happened because my parents were courageous self-leaders. And they reacted to adversity as courageous self-leaders do. They accepted what they could not change. They didn't throw up their hands and say, "I quit," and had some of these bad things happen. They accepted what they could not change, and then to the degree possible, they made a mid-course correction around those obstacles. They stayed laser-focused on their goal. The goal was raising these 6 kids. And they worked around the obstacle as best as they could, hammering away at that goal, raising these 6 kids. And that's all characteristic of self-leadership, how you respond to adversity. I was only 9 years old when this was happening. I had no idea I was being imprinted with these lessons, but I can see now as an adult how I was imprinted with them and how they played out in turning me into an astronaut. Let me tell you that story. Early in my life, I wanted to fly as far back as I could remember. Here's a picture of me when I was about 4 years old, looking at a book about jet planes. There were no astronauts when I was this young, but there were jets. I wanted to grow up and fly them. As I did grow up, an amazing event happened in world history. October 4th, 1957, 50 years ago, what happened? Sputnik. The space race started. I was 12 years old. I was reborn on that date. I became a child of the space race, fell in love with everything associated with space, with rockets, with astronomy. I was growing up in Albuquerque, New Mexico, and could indulge my interest in homemade rockets from the vast desert right outside my home door. And I was setting a goal, even this young, of someday riding a rocket into space, of being an astronaut. This is the first mark of self-leadership. We challenge ourselves in the extreme. We set very lofty goals for ourselves. There's a huge population that is here in their personal and professional lives, and now they're going to challenge themselves, and what do? They take a tiny little baby step. Why do they do that? They're safe. They know they can get here. Courageous self-leaders never do that. We know we can get here. What we don't know is, can we get out here? But we're going to find out. We're going to find out. We're going to reach deep down and see what we're capable of. It's really sad, the waste of potential in this world. These people behind us will go to their graves never knowing what they were truly capable of because they never challenged themselves. You can never know what you're capable of unless you challenge yourself. Think of it this way. We test military aviation, military planes, jets, to find the edge of their performance envelope. How high can they fly? How fast? How many G's they can pull? We all, individually, personally and professionally, have a performance envelope. But I'll tell you right now, it's a lot further out there than any of us think. any of us, myself included, that performance envelope is way out there. And the way we find it is by taking these big steps, these big challenges, reaching down, saying, hey, I can lead my team to a higher standard of safety. I can be safe. I can be a self-leader and influence the people around me to be self-leaders and make this team safer. I can do these things because I am a courageous self-leader. That is the first mark of self-leadership, is challenging yourself to ever higher and higher goals. And I certainly was doing that, as challenging myself to grow up and be an astronaut someday. As I said, I was testing these homemade rockets from the nearby deserts. Rockets? Not really. These things were pipe bombs with fins. It's amazing I didn't blow myself to hell and back with these things. Sometimes I needed a wind tunnel. I didn't have it, so I used my dad's car as a wind tunnel. If I saw this today, I'd dial 911. Sometimes I tested these things to the roof of my parents' house. A real dumb idea. The neighbors were sure happy to see me leave, and the fire department, I'm sure. Here I am setting up one of my creations for launch. Here I am legging it out after lighting a fuse. There's ignition, and there's detonation. I hear all the time, people hear I flew combat in Vietnam, flew 3 times on the space shuttle, and they say, wow, look at all that danger you lived in your life. Trust me, the most dangerous period of any male's life isn't whatever they do as an adult male. It's when they're a teenage boy. Because when you're a teenage boy, you don't have a brain in your head. And there's proof of it right there. Here's one of my successful launches. Here's one of my rockets parachuting back to the desert. Here I am recovering one of those rockets. I want to re-show this video. Note the young woman, about 18, 19 years old, walking off the screen to the right there. That is now my wife of 40 years. There's a woman who will never be able to say, I didn't know what I was getting into. Not when I have video like that. As you heard, I went to West Point, graduated West Point in 1967, went into the Air Force to be a pilot, test pilot, astronaut. Could not be a pilot because my eyes were bad. Ended up flying in the back seat of the F-4 Phantom, as I told you. Well, guess what? In 1967, if you couldn't be a pilot, you couldn't be an astronaut. End of dream, or so it appeared. But I can see I reacted to this news in a way that's characteristic of courageous self-leaders. I didn't throw up my hands and said, I quit. I had a goal. That goal was flying. My mid-course correction was, hey, if I can't fly in the front seat of the airplane, I'll fly as a goose in the back seat. If I can't be an astronaut, I'm going to get as close as I can. I'll work in mission control as a flight director, possibly. That's all characteristic of self-leaders, and that is encountering obstacles, and they're always there. Nobody ever has a straight shot for any personal, professional goal. There's always obstacles. Do you throw up your hands and say, I quit, or you navigate around them as best as possible, stay laser focused on the goal, and continue? 2 other things I was doing as an astronaut, excuse me, as an Air Force goose. I'll tell you how I ended up being an astronaut in a second, but 2 other things I was doing that are critical aspects of self-leadership. One is I went back to school and advanced my education, got a master's degree. Courageous self-leaders are never happy with their education. I'm not necessarily talking about formally advancing your education. I'm talking about an attitude, an open mind. I don't know everything, but I want to know everything. So you listen to other people. You'll go to company training or firefighting training opportunities. You'll read. You're sponges. Basically, you're always constantly trying to better yourself. Another thing we do is our best at everything. We pour heart and soul in the task at hand. We don't rationalize, when's this ever going to count? It always counts. Everything you're doing, everything you have ever done is going to count in your futures. So we constantly do our best at everything. For me, all of these characteristics came into play in a way I could not have imagined in 1967. 10 years later, 1977, the obstacle's removed. NASA changes the rules and says to be a mission specialist astronaut on the space shuttle, you don't have to be a pilot. Mission specialists are people that use a robot arm, do experiments, lift up satellites, things like that. You don't have to be a pilot to be a mission specialist. So all of a sudden that dream was back in front of me. I filled out an application. I sent it to NASA, and I was selecting the first group of shuttle astronauts 10 years after I thought that dream was over. Now let's summarize in text. And by the way, make sure you take this message back to your children on that do your best. For 10 years, I did my best as a goose, as an engineer, thinking it was never going to count toward being an astronaut because of my bad eyesight. It turned out it all counted. So all the children that you deal with, make sure they understand that. Everything they're doing in their life is going to count in their futures, just as it does for all of us. Okay, let's summarize in text here what we learned about self-leadership. How did it happen that a child with a goal of someday riding a rocket into space is 25 years later riding in a rocket similar to this, passing 200 miles over that exact spot in the desert. Here's Albuquerque seen from space. How did that happen? It wasn't luck. It wasn't destiny. It happened because I learned these lessons in self-leadership and practiced them. Self-leaders challenge themselves in the extreme, set very lofty goals. We accept those things we cannot change. We don't get bogged down or throw up our hands and say, I quit. We make mid-course corrections around the obstacles. We stay laser-focused on the goal. We constantly advance our education, and we constantly do our best. If I could distill into 2 sentences the philosophy of life by which courageous self-leaders live their lives, it's these 2 sentences right here. Success isn't some mythical final destination. It is a continuous life journey of challenging ourselves to ever higher and higher goals, searching for that edge of our performance envelopes as team leaders, as team members, parents, spouses, whatever. No courageous self-leader ever crosses the goal line, spikes the ball, says, game over, I won. Oh, we'll celebrate an accomplishment, but relatively quickly, we're going to say, hold it, I don't want to be here. I can lead this team to be safer. I can take them out here. I can lead myself to be safer and better. I can take myself out here. That's how it's done, finding that performance envelope. And I hope I just preached to the choir here. I hope you just all saw yourself in those characteristics. But please practice great self-leadership. Guard against that normalization of deviance. Leaders empower people. Don't allow them to slip into that passenger mode. And everybody remember, you count. Never fall into the passenger mode. Put your ideas, your concerns out there for the team and the leadership to consider. And when you do these things, you will take your teams to the highest achievable orbits of success and safety, as certainly as this rocket is taking her crew to new orbits. And I wish you Godspeed on that journey. Be safe. Bye-bye.